So we define a fraction of the data. So n is the sample size, and m is a number smaller than n. So the smallest, can also think about the smallest number of points in your of your observations, which would define a proper prior distribution. And the assumption O'Hagan does is we call this small m the so-called training sample. So this training sample, we don't want to specify as it is done in the intrinsic base factor, is a certain fraction of the likelihood function. And that's expressed here. So this should be proportional to the likelihood function to the fraction b. So if you do this assumption, then it follows, that's a little bit of calculation, that the fractional base factor is this ratio of marginal likelihoods. It's the marginal likelihood of f1 of x divided by f2 of x of b, where f1 b and f2 b I define now, that's my definition now, as a fractional marginal likelihood. And the fractional marginal likelihood is nothing else than the a ratio of likelihood of the informative part divided by the training part of the likelihood function, where we call this qi, where the qi is defined in the following way. So this is the fractional likelihood up to the fraction exponent of the fraction p, and pi is the non-informative prior, the usual Jeffrey type non-informative priors. You can have different type of non-informative priors here as well, but we always use the Jeffreys type of prior. So this QIB is nothing else than the smallest possible marginal likelihoods over this fraction of your sample. And by following this rule, so you go, that's where the usual marginal likelihood will be here. They have b equals 1. If you have b equals 1 and non-informative prior, then you end up what I have shown you before. This would be the marginal likelihood for the non-informative case. But this has the disadvantage that it cannot be interpreted as proper base factor. It will lead to contradictions. But doing it for a fraction of your likelihood, this leads to a proper posterior distribution, a proper base factor in this way. And so this is some kind of trick, isn't it? There you have the idea, the whole sample consists of a training sample and a non-training sample, and you average over the non-training sample by assuming a non-informative prior for your training sample. And it works, funny enough. So we get this nice formula here, and as I showed you before, and now going back to what we have done, this gives you this type of fractional marginal likelihood. So whatever the model is, you define a certain fraction b, and it has this form. And if you minimize this fraction, then you end up with this really nice formula where you see it's very close to the non-informative prior, but here it has the definition of fractional prior. So that's what we do here, and now we want to know how this applies to our data set, what I showed you before, the Swiss G and B and consumption. between 1970 and 93. That's when we had the data available. And again, the nice thing is that here is the Swiss GMP data series. And now you can calculate the marginal likelihood for various lags, like this is p equals 1, p equals 2, p equals 3, and well, actually this is one step too early. Here I can, what we are trying to solve at the same time is the model dominated by some structural breaks, what we've feared, because we had this behavior in the oil crisis and in the beginning of the 90s, or are some outliers present? And this will relate to this output, but I have to show you first as a different table. I hope I find it now. It defined two hypotheses, that we have a breakpoint at time m, and m could be between k plus 1 and t minus k, and then we have a hypothesis that there is a breakpoint in the whole time series. So this is a specific breakpoint, and that's in the whole time series. So H1 is nothing else as the union of all these hypotheses up here. And if we do this, and you can just follow Bayes rules and the posterior odds ratio, if you're senior, then you transform the prior odds ratio, which is called here now P0 to P1, to a posterior odds ratio, which is called here the likelihood, the ratio of the null hypothesis given y to the alternative hypothesis, and the data summary comes in here by this Bayes factor, which is this thing here. And if you do this and plug in their data as I have shown you before, then this is the posterior odds ratio. So it's prior odds ratio times this type of Bayes factor. So that's one way of extending the model. Another way of extending the model is not assuming homoscedasticity, we assume heteroscedasticity. So it's the same model as before. We have a breakpoint at a certain point in time, and we have two residual variances. And again, for such a model, we can calculate the marginal likelihoods. So the first part has m observation, the second part has t minus m observation, and you see the non-informative model would be a product of these two marginal likelihoods. And again, you can calculate this marginal likelihood by the formula which I just gave you, but just extending it. Now we wanted to know how good is it if we use this type of procedure. And for this procedure, we used a simulated example first, and then we looked at the other one. So we said, well, what's about the time series which consists of 200 observations, and the first 100 are autoregressive process of order 2 with a positive coefficient in the first place and then a negative coefficient, and the errors are distributed spherically. So that's the output now, what I'm showing to you. So you see here the simulated time series. The first 100 observation we have the smooth autoregressive process, and then we have this irregular type, and we can now employ different autoregressive models of order 1, order 2, order 3, for instance, and then compare the marginal likelihoods. Now we can really calculate it for every time point here for different breakpoints. And what you see here is the leg 1 model is shooting up to 100 and goes down as well. So it's already indicating something is happening around observation 100. And if you look at the leg 2 order, then you can see that this cusp really culminates here at the observation 100 and goes down very rapidly. And the same behavior you find for leg 3. But this is not enough. You can also compare the marginal likelihoods across these models, and then you see here the maximum is this is a S plus output, which is difficult to get a common scale. Here is minus 350, and here's minus 310. And it's also this leg 3 model is also close to 310, but here you see it's a little bit higher for the leg 2 model, and it picks this breakpoint right away at this in the middle. And I think this is a clear indication that this procedure picks up the right breakpoint. What are classical alternatives? You have a Q-sum square test, or you have some kind of lambda ratio, likelihood ratio test, and so on. If you compare those graphical outputs, which is possible, but they're much more complicated to justify from a classical philosophy, with this output, you will see you never get such sharp analysis as you get by this marginal likelihoods. And now what we wanted to do is, sorry about that, we tried to apply this for our Swiss time series. So here is the non-stationary, well, that's the next thing which we'll talk about it, the non-stationary time series and the stationarity, how we test for that. But we want, since we are independent of the stationarity question in Bayesian modeling, we can apply this procedure here for this type of series, and later on we will do it for the first differences. And still we can ask, do we find some kind of structural breaks here? And you see that the data are not very conclusive. The maximum is taken by an autoregressive model of order 5, and the only thing which turns out to be similar, close to our breakpoint is the oil crisis in the beginning of 74, end of 73 here, which comes here up as a spike. So the model selection in this case would prefer an autoregressive model where we would say at the beginning of the 70s we see a break, but probably not at the end here of the time series, because the 5 years which were available here of 4 years are not enough to justify a breakpoint model here. So we can do the same thing for the 4th differences, and this is clear in our stationary time series. And the stationary time series here gives you a maximum at leg 6, and it shows you a similar behavior what you have already seen for the level data, that probably if you think there was a break, it was here in the early 70s, but nothing can be seen later on. And this peak here comes out quite clearly in most of the pictures if you go up with the leg order large enough. Now let's see what their consumption is telling you. So we have, since it's a quarterly time series, we took 4 differences. And again, that's the first picture is the time series you see here. Then you see like order 1, 2, and so on. And again, leg 6 seems to be the appropriate order for this model. And what we found out is if you look for this breakpoint model, then the model with heteroscedastic variances, so with different type of error variances in those 2 regimes, will be preferred. So also we see here a breakpoint model and in the consumption, and if you look at the non-stationary time series, we see a similar behavior. So it seems to be that this model is justified. So this is one way of doing model choice. Now I want to come to multivariate modeling, and let me quickly show you in the last 15 minutes. I know it's late, but I think it's just now an outlook for the last lecture where you can will show you how to apply this for multivariate modeling in Gibbs sampling and the ARCH setup, where the things can be much more complicated. If you have a multivariate time series here, a k-dimensional time series, y1 to yk, and t observations, we can write a so-called vector autoregressive model of order p here. And this model would look like for the following: alpha 0, which is a vector, a1 is a coefficient matrix yt minus 1 to ap yt minus p. So everything similar what you have seen in the univariate case, except that now this is a vector and there's our coefficient matrices. And the error term now ut, it follows a multivariate white noise series where sigma can be now a covariance matrix of channel form. So the parameters which have to be estimated are now summarized in this theta, which is from alpha 0 to alpha p, and sigma here. And what you can show here, sorry about this bleaching here, but you can write this model as a multivariate regression model. And if that's too quick for you, a good textbook is Lütkepohl, 1993, with multivariate time series, which explains that. So you can write this yt as a multivariate normal distribution with coefficient matrix B and vector ct. So the ct is now the data vector and B is now their coefficient matrix as we do it for simultaneous equation systems. And the ct is now a vector consisting of a 1, of a constant, then the lag vector. This is a vector and this is a vector here, and this is also a vector here. So it has now a much more longer structure than in the univariate case, and B is now this coefficient matrix which consists of all the blocks, vector block 1 to block AP. And interesting is, if you follow all this, then in a classical framework you can do a multivariate least squares or maximum likelihood estimation conditional on their initial observations. And you have only to go now to make the step from this vector equation to a multivariate regression system. So the multivariate regression system looks now the following. You write the matrix Y from Y1 to YT, where Y is the first vector time series observation to the last vector time series observation at time t, of order k. So this is a k times t matrix. Then you have b times c. So b is the coefficient matrix now of the vector autoregression, and c is the data matrix. And the data matrix again follows a rather complicated setup, but still we are in this linear framework where ut now is a matrix error term and follows multivariate normal distribution. If you have a system like that, you observe that b is now in front as coefficient, not back as we have done it. And if you want to have it in our familiar regression system, then you just have to transpose this multivariate equation. And if you write it then now as y prime is c prime beta prime plus u prime, and if you feel more comfortable with this, then you can have the multivariate OLS location as written as c times c prime inverse c times y prime. And this gives you the OLS estimation of this vector autoregressive system. So that's the way how we can generalize this univariate autoregression to a multivariate autoregression. The only difference now is we need a generalization of the Bayesian model as well. And the generalization of the Bayesian model is the so-called normal Wishart regression model. So far we had only a normal gamma regression model. Now we can go one more step in multivariate directions and have a multivariate Wishart. So what is the difference here? We have now a Kronecker product for the covariance matrix. So sigma Kronecker IT, and that's the sigma which you have seen with this intrinsically unrelated regression matrix with what was Bill Griffiths talking to you. And this can be estimated in different models, also very complicated. And I think it was Arnold, you and Henry Style who invented all this sewer stuff a long time ago, wasn't it? So here is the inventor of some methods. So that's really good to say. And the non-informative prior for this type of normal Wishart distribution is the Jeffrey prior, which is proportional to the determinant of this matrix sigma here, and in the exponent you see the dimension of the model. So again, we will be interested in testing, and testing, for instance, the multivariate order of such a process. And what I want now to convince you in the last minutes is the structure of the formulas stay essentially the same if you look now for test. If you look for the test, the base test and the associated Martian likelihoods, that's the formula. That's the Martian likelihood here. So again, you have essentially 3 or 4 terms. So you have the matrix x prime x. You have the residual variance, which is now a determinant of the residual covariance matrix u prime u hat. And here, if you want to know what u hat is y minus x b hat, and b hat is now the multivariate OLS estimate, not the univariate one. So that's the generalization. And here you have not the univariate gamma function, but the so-called multivariate gamma function. And the multivariate gamma function is essentially a product of m univariate gamma functions. And then you have in front here sitting always this pi to a certain exponent which comes in here and in front of here as well. So pi is some kind of constant you have to multiply these 3 terms. So this is the simple Martian likelihood function. If you do the same thing for an informative model, then just briefly in a normal Wishart model, we think about this as a normal gamma model, with the only exception that now the residual variance is not anymore scalar, but a variance matrix. So we have to generalize this scalar, which was the scalar for the gamma function, or the chi-square, to this Wishart distribution. And the structure stays the same, as you see here. It's only the dimension of the model blows up. So we have a normal Wishart conjugate class of family, where you have a prior B star, H star, which determines the regression coefficient part, and then we have the second part, sigma star and n star. N star again is the degrees of freedom, but sigma star is now the scaling matrix of the Wishart distribution. And if you now look how this marginal likelihood would look for this multivariate regression or the multivariate time series case, then here you see again the formula which comes in these three parts I just explained you before. You have a ratio of determinants, if we start now from the back, a ratio of residual sum of squares, which is the sigma star and the sigma double star, so it's the prior sum of squares matrix now, and the posterior sum of square matrix. And then you have a ratio of gamma function, which I have now called constants, depending on the posterior degrees of freedoms and the prior degrees of freedom. And then you have always some kind of pi's or 2 pi's coming as another constant here. So what are the ingredients? What is the new thing about here? You know how to calculate the posterior variances. This formula stays the same. The only difference here is how to calculate the posterior sum of square matrix, the sigma 2 star. And again, the sigma 2 star is built up, as in the univariate case, as the sum of the prior sum of square matrix plus the sum of square of the OLS procedure matrix and a discrepancy term. Discrepancy term delta, and the discrepancy term is written here. It has the same structure essentially as we have seen in the univariate case. The only difference here, it's now not a number but a matrix, because beta hat is a matrix and B star is a matrix. And you get also penalized if now the whole system as a whole lies far away from your prior location than what the data are telling you. And H star is the same matrix, the posterior position, adding up the data and the prior positions and the posterior degrees of freedoms is essentially the same. So maybe it's a nice thing in the whole normal regression framework that we can extend all this formula easily to the multivariate case. And what we did now for the informative case is, if we have to specify a prior distribution, then what we do is essentially assume diagonal structure for all the time series involved in a multivariate system. So what we have done in the univariate time series, we do now for the multivariate time series. We assume a tightness structure for all of the time series individually and then multiply it. And that's essentially what will go into our prior specification as a default. You're always free to change it, but if it, as a simple default value, if we talk about the so-called BVAR modeling. So that was called BVAR in the 80s when Litterman and Sims and the one developed all this methodology. So in analogy of this, we have done that. And so in the last few minutes, I will show you can do the same thing for a breakpoint model. So if you're interested in breakpoints or in outliers, you can do the same procedure I just explained to you for the univariate case. For the multivariate case, you split in 2 parts, and then you can assume either a homoscedastic covariance structure or a heteroscedastic variance structure, calculate the marginal likelihoods for this model or for the other model, and compare them and find out what is the better model. And this is, if I want, to show you some empirical results. That's exactly what we did with this two-dimensional simple consumption and GMP model. So we calculated their marginal likelihoods for non-informative priors, for fractional priors, and for informative priors. And we did the model choice in the same way. So we calculate for different orders this marginal likelihoods, and then we looked what is better. Is it what order is fitted? And now you see the order is now reduced to leg order 2. So in the univariate cases we had up to leg order 6, but that's a typical feature of multivariate modeling. The leg orders become much more shorter because much more coefficients are involved, and this likelihood penalizes really the number of observations. So you see, the order 2 is picked by the funny enough, by the non-informative prior. We tried this, even it's not recommended, but for the informative prior and for the fractional prior, we did that as well. And then you can also ask, are the breakpoints available, or is it present or not? And if there are breakpoints, is it for equal variances or unequal variances? And funny enough, we find strong evidence that if there was a breakpoint, then the equal variances is preferred to unequal variances, but it doesn't seem to be the case that in the multivariate model we had the breakpoint, because if you look here at the log marginal likelihood for the informative prior, I think it was preferred. I think or it's not the case. I think it was almost the same. It was a little bit better for the breakpoint model than for the non-breakpoint model. So again, also we concluded here by a simple Bayes test that a breakpoint model seemed to have been a better fit for this joint model of consumption and GMP in Switzerland than a non-breakpoint model. So I think now we are pretty much coming to an end. So this is really the last slide now I wanted to show you. This was tour d'horizon, very quick. I apologize for the last few minutes, but it's just to whet your appetite. You are really free to model now any complication or any generalization of such an approach, and try to fit the best model and test it by this principle, by Bayes factors or marginal likelihoods. Thank you, and I hope you enjoyed a long day with me. Thank you.